Hello everybody, this is Michael again. In today's video, we're going to look at the Crank-Nicolson analysis for finite differencing. This is going to be a continuation of all that we've done up to this point so far, where we were looking at essentially, how the heat diffusion equation was developed, and then we got into finite differencing after, seeing it in rectangular and spherical coordinates. And this is going to be another way to approximate a solution for the temperature as a function of the position and time increments. And we're going to basically look at what we would do with the Crank-Nicolson analysis as opposed to the von Neumann analysis. Now, what's different about this one is this is going to be an implicit method, and the one that we had done before with the von Neumann was an explicit method. Now, what does that mean? The explicit method that we had done with the von Neumann is we looked at some temperature, and it was at some position, and the temperature that we were trying to determine, it was n+1, which was the time ahead, was dependent on the time that we knew right before it. So the temperature at some position that we're trying to determine is equal to the temperature at some time before it, and that's what we were trying to determine. So the difference with that now with the Crank-Nicolson analysis is it's an implicit, because we are going to actually look at this as the average of the time ahead that we're looking at and the time right before it, and it's just going to be a matter of taking the sum of those two and dividing that by 2. So if you guys recall, we had this finite differencing equation right here where it was Tj of n+1 minus Tj of n was equal to our alpha, which was our heat diffusivity constant for our material, times the incremental change in our time, divided by the square of the increment of position, and that was all multiplied by Tj plus 1 position some point, and then we just kept the n consistent through. It was minus 2Tj was the position that we're looking at, and then the position right before it as well. So it was just Tj minus 1n. So essentially what you do this time around is you still have this whole entire term, but you also add these Tj plus 1, j minus 1 terms with an n+1 on that side, and you divide that by 2. So what's going to end up happening is, if you defined this whole entire equation as equal to r, well, the new equation would have a 2 right there. So it would be the heat diffusivity times the incremental change in time divided by 2 times the square of the incremental change in position. So if I was to actually write this out for you guys, it would be, now you have your Tj n+1 minus Tj n is equal to this whole thing being r, and now you would have your Tj plus 1 n+1 minus 2Tj n+1 minus, or plus, this is a plus by the way, Tj minus 1 n+1, and then it would be summed with the this, basically all this, if you just copied it down, plus 1 n minus 2 Tj n plus Tj minus 1 n, and we already incorporated into that r the 2, so it's going to be the average of those two. What you end up having to do is basically distribute this r out, and then you would move all the n+1 terms to one side, and then move all the just the regular n terms to the other side, and that's all you would do. So let me go ahead and do that real quick for you guys. So you would have Jn plus 1 minus Tn. And as you guys can see here, it turns into a really, really big equation. And like I was just saying, you have to just move these n+1 terms here, and you could just keep those there. So it's pretty easy with the algebra. Wherever you see the minus, just make it a plus, and then where there's a plus, make it a minus. So you would have basically your tj n+1. Then you'd have minus r. And then you, of course, to get this one over here, you would just add a plus tjn. What would end up happening here is you can see that this term and this term are in common. They have the n+1 and the j, and so you would be able to combine that. So in order to keep things relatively, the same, I would have the j+1 the first term, I would have the j in the middle, and the j-1 at the end. So I could just put minus rtj+1, and then what would end up happening is you'd factor out the tj. You have plus tj n+1, and then it would be 1 and then plus 2r right there, and then you would just have the last term here. So you have minus rtj-1, and that would be n+1, of course, as well. And you would do the same thing on this side, essentially. You'd have that j+1 term carry on down. And then you would combine the tjn terms, because those are going to be the ones that have something in common. So you have plus your tjn, you have 1, and then minus 2r, because there's a minus 2r right there. And then you would have your last term right there, so it would be plus rtj-1 at n. And for a second here, I'm actually going to pause this because I'm going to move all of this up here because I'm running out of room, and then we will go from there. All right, guys, so I'm back. What I ended up doing is I copied that equation that we had derived earlier from, taking the average of the two, the time step ahead and the time step before for this Crank-Nicolson analysis. So I basically wrote that equation up here. You just saw it. And what I ended up doing is I rearranged some terms, so what was in front, I basically put, or what was behind, I put in front, and what was in front, I put behind. With these two terms, I flip-flopped them here just so it looks a little bit nicer and whatnot. And also, if you remember, there was actually some terms here that I accidentally forgot to put the n+1 or n. I went ahead and corrected that. But the thing is, with what we have here, is it could actually be simplified even further, and it's going to actually tell us and show us how, unlike what we had found with the von Neumann analysis, where we lost some stability when our R value was greater than 1/2, what we're going to find with this is that we can actually relatively, or we could have our stability stay for any value of R, and you'll actually see that here in a second. But it requires me to actually take what we have here and simplify it further. If you guys recall before from what we had done with the von Neumann, we used those sinusoidal functions that are developed from the Taylor series expansion, exponential of cosine and sine waves. We had that e to the ikx, and that was equal to the cosine of kx, and it was plus I sine of kx, and then we had that e to the negative I kx, and that was equal to, you know, the opposite there, minus I sine kx. I'm supposed to put the kx's in, yeah, okay, there's a kx there. And we basically combined those terms right there, and we ended up being able to actually get some more useful equations out of that for our finite differencing formula. So we ended up getting that the cosine term, because there was a cosine term and a sine term, but we actually did not need the sine term for our purposes. So it was the cosine of kx was going to be that e to the I kx plus e to the negative I kx all over 2. And what we ended up doing here is we actually utilized this earlier to put our equation in terms of these cosine functions and whatnot. So by utilizing this e to the I kx to cancel some terms. So what ended up happening is that tj part ended up staying, and then the plus 1 would add, because it would be the same thing where when we took our function here, if you guys remember, it was the temperature at some k value was the e to the I kx, and that was multiplied by, let me move that out of the way, negative alpha k squared t. And then what we ended up doing is actually we changed that x to a j delta x, and we changed the t to our n delta t, because it of course can change, and we could find our position and whatnot according to, you know, what kind of increment we wanted to use and to find at the position within our object. And we ended up saying, okay, well, if that's just the temperature at some k value for the time, and we did the j plus 1, we could carry the part of the time over, and we notice that the j term would be plus 1, so it would be one step ahead incrementally. Well, we already said that in the previous video with the von Neumann analysis that it's going to be the same thing as taking that e to the I k and doing the j plus 1 delta x, and then just saying, okay, well, that's going to be the same thing as the I k j delta x, and then I k delta x. And then we would end up noticing that at the position that we're looking at, that tj, we would have the two terms combined, the one with the alpha right here and with the other one, and then that plus 1 term would be the next part. So we would end up actually subbing that in to our equation as well, and then we would be able to expand it in terms of these e to the I k j delta x's as well, and then factor them out. So what I'm going to actually do here is I'm going to erase this since it's up there. And what you would notice is that if this was tj, and that all of these are tjn plus 1, you would end up being able to actually factor that out. So it would be tjn plus 1, and then we would have this negative r here, and since the tj already got taken out, we would just have that ik, or e to the I k delta x, and then we would just have the 1 and the plus 1 plus 2r. Get this out of the way too. I have a tiny board here, not as much to work with. And then we would do the same thing for the last term, and then it would be minus r, and then since it's behind now the position, then we'd have e to the negative I k delta x. And the thing is that, just for the sake of time, I'm just showing you this, how this would actually develop. I'm gonna go ahead and skip ahead of time, and you know, for the simplification processes, and so I'm not showing all this crazy algebra. I'm sure that if you are able to understand this video, you could do the algebra yourself. So that would be the one side of the term here. And I'm not going to do the same thing on the other side. It's going to essentially come out to be the same principle there. So what we realized is that e to the I k delta x and the e to the I k delta x right there is that you would actually be able to see that this would, here, let me put a plus there. This was actually equal to that cosine function kx, where we saw that it was e to the I kx, and we saw it was e plus e to the negative I kx. And what would end up happening is that when you would combine those two right there, maybe this was minus, I believe it was plus. So what would end up happening there is you'd be able to separate those for having them just as 2r right there, because the r would be in common, and then you would also have this replace the e to the I kx delta x and I to the kx, you know, delta x of course. And then you would have that be a function as, you know, if you were to actually have this, it would actually simplify to 1 minus 2r, and then you would have 1 minus cosine of kx. And then the only difference would be the other side. If you were to do the same thing, it would be 1, and then you would have plus 2r, 1 minus cosine of kx. What would end up happening is these two would be divided. You would have your tj right here, and you would have your tj and plus 1 right there. And what you would end up being able to determine here is that this would actually not implode in the same way that it would previously, is because this term is always going to be positive because it's between negative 1 and 1 right here, and multiplied by 2. And then right here, it would, of course, you know, for any values of r and k's right here and x's, this would actually end up being smaller. So what's end up going to happen is that for any values that you put in, it's actually going to be less than 1 of whatever you get in here. And so it's actually not going to implode like it would before with the other equation that we had done. So what I went ahead and did, and I actually expressed this equation, how it can be actually modeled with a matrix right here. So for any value of tj you have from the very beginning of your boundary condition, where it starts, to the very final, that's why I put, you know, t naught to tj final. That could be, you know, it depends on how long your block in this case was. You know, of course, in the initial time I had from 0 to 9 or 10 subsections there, but it could be of any arbitrary length. So for example, if you had t1 here, well, what would end up happening is you would have t1 right here, and that would actually give you t2, and then you would actually also put that 1 in, so that would be tj1, and then right here it would be to the left, it would be on that side. And what you would end up doing is you would actually be able to put in your equation there. So what would end up happening is it would just be a series of 1s and 0s, and you kind of would see a pattern there. So if you had 1 there, it would be negative r to tj at 2 plus 1, and then you would have plus 2r, and then this j would be tj at 1 because it's just 1 there, and plus 1, and then minus, this would be 0 because 1 minus 1 is 0, and like I was saying, it's the time before. That's why, and you already know that. If you're putting something there, let's say some kind of surface that's 400 Kelvin, then you don't really need to model that equation or to be able to, you know, determine it through any kind of analysis of any sort that we've used so far with finite differencing, Crank-Nicolson, von Neumann, any of those kind of things, because you already know where your temperature is at one end of your object, and then you could know the same thing at your other end of your other object as well. So you would have these, and you'd be able to put these values in and get an equation that explains that what's going on with the temperature at a time ahead or a position ahead, and that's how this could help you. By that way, I also want to add, it would actually not be, because you're looking at that position at that time ahead in comparison to the time before it, so this would actually just not even really need to be there because it's implied. So you would have that, and the thing is that you can just finish this off right here. So you would have that, and then minus RT at 0. And that's how that would look. And then you would do that for 2, and then 3, and so on. And then what you would end up seeing is this would end up being 3, and then plus 2R, and then 2, and then R1. And then you'd see that this would go up, and this would go up incrementally exactly as such. And then that's the pattern that you would see once you would do this matrix multiplication. And that's pretty much it. I thank you guys for watching.